signal coming out from the controller. So how is the controller? We take pressure sensors, we have pressure sensor assembled on the work port of the directional valve, and then there is a logic here where basically with a low pass filter, I use a low pass filter just to select which is the highest value pressure, and then just to select which pressure sensor to use for that particular operating condition. So the output of this will be P, which is PA or PB, and this will feed a high pass filter, which serves as just to isolate the oscillatory part of the signal. And this goes into a PID controller, which gives a signal which is superimposed to the signal to the operator command in order to counteract these oscillations. And this methodology is implemented by using a gain scheduler. And the gain scheduler is indexed by the low pass filter pressure, which gives an indication on the load conditions of the machine, and by the operator command, which indexes the operation of the machine. And once the operating condition is identified, this helps the PID to select the proper parameters for that particular operating condition. So before going further, I would like to introduce the reference machine, which is the experimental setup I used for my entire work. And so it's a truck loading crane, as you can see from this picture, and it is assembled and instrumented here at Maha. And we can see the main actuator. So we have the main and outer boom actuator and a few telescopic stages. The hydraulic system of the crane that you can see here has in this close picture of the hydraulic system. So here is the original hydraulic system. And in order to show the flexibility of our controller strategy, we also equipped the machine with an alternate control block, which I will explain right in the next slide. So the original hydraulics of the machine, it's a fairly standard and simple hydraulics where we have a open center valves. And so one peculiarity of this way of controlling this machine is that it's fairly simple, fairly straightforward, because we just need one input from the operator in order to control the motion of the machine, because now the 2 meter in and meter out edges are mechanically linked. And here in this picture you can also see the location of the pressure sensors, flow meters, and thermocouples that are present on the machine. This is a partial schematic of the hydraulic circuit of the new block valve, which is in particular a load sensing independent metering block valve. So now the peculiarity of this motion control system is that now we can control independently the 2 edges of the actuator, so the meter in and the meter out. So this poses a challenge in the controller, because now, in order to, for example, to extract the cylinder, we have to command SP2 and SP4. So SP2 will be the meter in edge, and SP4 will be the meter out. So we need always 2 inputs for controlling the machine. And the same story for SP1 for the retraction of the cylinder. And here the challenge is that the load conditions, they can be different on the machine, and so depending on the load condition, the inputs to the 2 valves, they have to change. So in the case of a resistive load where the force of the load is in the opposite direction of the motion, we don't need to basically control this one. So we can just fully open SP4 and partially or fully, we can control SP2 in order to control the velocity of the actuator. When the load becomes overrunning, now we still control the velocity of the actuator by using SP2, but now we have to control the meter out edge of the cylinder in order to introduce a counter pressure to support the load, to avoid cavitation in the other chamber of the cylinder. So this is a small, I don't know if it's small, it's a challenge I have to address. So if you can see here now the same controller strategy as before, where this top part is the same as before, where we are controlling the meter in edge in order to control the velocity of the actuator, but we are also controlling the meter out. And here it's a simple logic of this controller. So here with the pressure sensors, we do the balance in the cylinder just to recognize if the load is resistive or overrunning. So if it's resistive, we just fully open the emitter out. If it's overrunning, I try to track a pressure reference. So I give a reference in pressure to the chamber, and I try to not to go below that pressure in order to avoid cavitation, so just to support the load. And my entire PhD was supported by, and all the results you will see in this presentation are supported by a model activity, a modeling activity of the machine. And I mainly used MSIM to model the hydraulic and the mechanical parts of the machine. So here you can see very quickly a few screenshots of the modeling of the kinematics of the machine and also the valve block. Here you can see two different approaches. So I have an high fidelity model for the directional control valves, but I also have a simplified model in order to save computational time to perform optimization, as we will see later. And I also accompany this activity with some experimental validation of the model. And here you can see just an example of a validation for the extension and retraction of the outer boom. Another important component of this machine, which I spent quite a few times during my PhD because they strongly affect the dynamic response of the machine, are the counterbalance valves. So here again you can see the model of the detailed model in MSIM again of the counterbalance valves. And here you can see the validation activity I conducted for validating this model. And so here it's just a simple screenshot of my model where we can see different super components in MSIM. So the machine kinematics, the counterbalance valves, and the block, and also the supply of the machine. And everything, the controller is implemented by using Simulink and by using co-simulation between MSIM and Simulink. So, closing this side about the reference machine, now I want to go back to the controller. And as I said, dynamic pressure feedback and gain scheduler are nothing new so far. The real innovation of this research is how we populate the gain scheduler. And we do this by using an optimization process. So as every optimization, we have an initial step where just initialize the parameters. And then we have the operation of the machine, which can be a model of the machine or can be the actual experimental setup if it's available. In the second step, we have the cost function calculation. And the cost function calculation, as we will see later, it's very important because it's a quantity which is a representative of the oscillation content of the particular operating condition. And this is something we want to, for example, in my case, I want to minimize. In the third step, we have the optimization itself, where here we just, we can use any algorithm. In our research, we used an extremum sequence algorithm, which is a gradient algorithm to optimize the parameters, meaning that we want to drive the operating condition to its minimum. In our case, is minimizing the oscillations. And then the output of this process is a new set of parameters for the controller, which are fed back to step one, and all the process keeps running until we reach convergence of the cost function, which means the cost function is minimized. So part of my effort was done in making this approach more general, and I want to focus on the cost function calculation. And again, as I said, it's very important because we want to achieve two main goals with this cost function to minimize. We want to minimize oscillations, but we don't want to affect the operation of the machine too much. We want to keep the speed of the machine in order to not affect the productivity of the machine. So in order for you to understand better what I did, I want to show you how the cost function was previously calculated. And for doing that, I use this example where we have the extension of the machine with an accelerometer placed here. And if we give a step command to the machine, this is what we get as acceleration of the boom, which is the blue line. Now, if we interpolate this blue line with just with a polynomial here, we get this green dotted line, which is what we call our optimal profile for the acceleration, which is the profile, the optimal profile in the case we have no oscillations. So naturally, the difference between the blue and the green line is our cost function, which is what we want to minimize. And I want to spend a few words on this cost function calculation, because it's a very clever way to define a cost function, because as you can notice, the acceleration oscillation is not around zero. He has a varying offset. And this is because the accelerometer on the machine can actually also feel the gravitational acceleration, which intrinsically is giving also an information on the position of the boom. So by minimizing this area here between these two lines, we are actually minimizing the oscillation, but also maximizing the speed. So it's a very clever way. But unfortunately, he poses some limits to this application. First, because we need an accelerometer, and second, because we need to know the operating condition a priori in order to generate this ideal profile. So my effort was to try to find a new formulation in order to make this approach general. And of course, we have to avoid the use of the accelerometer. So now what I did, I use what's left, which is the pressure signal. So in order to minimize the oscillation, I used the high-pass filter signal, which gives the oscillation content of the operation. But at the same time, I also use the controller action, which is something we want to also minimize. Because as I said, this machine, they work in open loop. So the more the controller is disturbing the operator command, the less the machine is tracking the operator command. So this leads to a multi-objective function optimization. And now we have to generate, of course, in order to apply the extremum seeking, a single objective function. For doing that, I use this formulation here, where alpha and beta are just weights. And in my case, I use the same number for alpha and beta, but if you want, you can give more weight to a objective function with respect to the other. And the bar here means just that the cost function is normalized. So I implemented this new cost function and I ran the optimization. And in order to see the effectiveness of this new cost function formulation, I ran two different experiments. And these are the two cases I'm presenting here. So the extension of the outer boom without load and the extension of the main boom with load. So for the first case, here we can see the result of the optimization with the parameters. And now we are comparing the acceleration, the directional valve control command, and the pressure measured on the workboard. And so these three lines, of course, the first one, the blue one, is without control. And the green one is with method A, which is the method that uses the accelerometer. And the second one is method B, which is the one I propose that does not use the accelerometer. And as we can see, the performances are very similar. In terms of number, the method A decreases the oscillation by 81%. Excuse me. And method B reduces the oscillation by 78%. So we are very close. And also in this video, you can see that we are, while effectively reducing the oscillation of the arm, we are not slowing down the motion of the machine. For the second operating condition, again, we see similar results. And again, we have acceleration, control, and pressure measure. And again, for method A, I measured 77.5% oscillation reduction. And for the method B, which is the one I propose, is 68%. So they are very close, but now the new method does not need an accelerometer in order to run, and also can be left on the machine and keep optimizing the parameters of the controller over the entire life of the machine, so taking care also of the wear and the normal changes of the machine. Coming back to the optimization process, another effort I have done is the demonstration of the application of this optimization process directly on the experimental machine. So in the previous work, this method was applied by using the model. And here you can see a plot from the Cristofori thesis. And as we can see, the method is working because we are converging to the minimum of the cost function. But as you can see here, we have a huge number of iterations, which is something not implementable in real life when we want to optimize the controller on the actual machine. So my effort was to try to formulate this strategy for being applied on a actual experimental setup. And of course, details around the thesis, and in order to show you results from these auto-tuning experimental activity I done, I'm proposing these two operating conditions here, so the main boom unfolding and the stop of the main boom after the folding. And so for the first operating condition, here we can see the result of the optimization, where we have here the cost function and the two parameters for the controller. And as you can see, first, after about 50 iterations, we reach the convergence or the minimization of the cost function. So now, by using a small amount of iteration, we can actually see the minimization of this cost function. And just a few points from this plot here. In this point, of course, the cost function, as you can see, has a huge value. That means that the machine is not even responding to the operator command because the parameters are not optimized. As we go along with this optimization, the machine starts maybe responding to the operator command, but we still see some residual oscillations. And as we move to the end of this optimization, the machine is actually, the oscillation content is minimized. For the second operation condition, we have the similar plots here. Of course, now the cost function, because remember, this is something experimental, so we use sensor to measure the cost function. And this particular operating condition, it's much more noisy, so it's more difficult to obtain a clear convergency. But still, as we can see here, at the beginning of the optimization, the response of the machine is very oscillatory. I don't want to say unstable, but oscillatory. As we go to the end of this optimization, we see that the machine is actually behaving much, much better. So the optimization process is able to counteract these undesired oscillations. And this is the side about the energy consumption I told you in the outline. So of course, this dynamic behavior is not something that you find in commercial machines. This is something we did on our machine in order to show energy saving potentials. And in particular, as I said about the counterbalance, they greatly affect the dynamic response of these machines. So what I did, I replaced the original counterbalance of the machine with some adjustable counterbalance, and I tried to evaluate how much is the effect of this